The distance between a rat and a city, eternal Aqualung. Script 3. The Ocean Floor, a 30-minute documentary narration. Part 3 of the series, by Richard C.J. Young. Sejong. Part 1. The distance between a rat and a city, a sealed chamber. A rat. A hollow fiber membrane contactor, extracting dissolved oxygen from recirculating aerated seawater. No compressed gas. No surface connection. $150,000. 6 months. One binary question. Does the metabolic loop close on a living mammal? Everything in this script is downstream of that experiment. If the rat does not breathe, none of this exists. If the rat breathes, everything here becomes a question of engineering, funding, and time rather than physics. Script 1 made the case for why the experiment is worth running. Script 2 described what follows if it succeeds. This script follows that thread to its end. Not the end we reach in 5 years. The end we reach in 50, if the foundation holds through every phase of work that follows. The tone shifts here. Script 1 was cautious. Script 2 was technical. This script is speculative in a specific way. It describes what is physically possible given validated technology, not what is planned or funded. The word will does not appear without a caveat. The word could appears frequently and is meant precisely. This is not a promise. It is a map of the territory that opens if the foundation holds. The foundation is always the same. One rat, one sealed chamber, one membrane contactor, one question. Aquarius and what it actually proved. Part 2. Aquarius and what it actually proved. In 1986, NOAA deployed a pressurized underwater habitat at 19 meters depth off Key Largo, Florida. They called it Aquarius. It ran continuously for 26 years until 2012, when budget cuts forced its decommissioning. During those 26 years, Aquarius hosted over 100 missions. Marine biologists lived and worked on the reef for up to 2 weeks at a time in saturation, their bodies fully equilibrated to ambient pressure, diving directly from the habitat without decompression stops. They logged more productive hours of reef observation from that one station than all the ship-based research programs in the same region combined. The data directly informed coral reef conservation policy across the Caribbean. It was one of the most productive underwater installations ever built. It was decommissioned because of gas. Not because the science was exhausted. Not because the structure failed. Because maintaining the compressed gas supply, the oxygen and nitrogen mixture that kept the habitat pressurized, that supported the saturation divers, that ran the life support systems, cost more than NOAA's budget could sustain, without dedicated congressional appropriation that never came. The annual operating cost was approximately $3 million. The majority was logistics. The support vessel, the gas transfer systems, the personnel required to manage the compressed gas supply chain from the surface. Remove the surface gas logistics and the operating cost drops by an estimated 60 to 70%. At that cost, Aquarius does not get decommissioned. It gets replicated. This is the specific, concrete, historically documented consequence of not having what the tow sled's core technology provides at station scale. The hollow fiber membrane system that keeps a military diver alive for 8 hours on a tow sled is the same technology, at larger scale, that keeps a 4-person research habitat alive for a year without a gas ship in permanent attendance. The components are the same. The physics is the same. The only difference is the number of membrane modules running in parallel and the size of the power supply. Aquarius was not shut down because undersea habitation is impossible. It was shut down because the gas logistics problem was never solved. The tow sled, if the rat breathes, if Phase 1 validates, if the production hardware matures, is the first step towards solving it. Everything this script describes is downstream of whether that first step holds. The precedent. Part 3. The precedent. Aquarius was not the first. It was the last one standing. In 1962, Jacques Cousteau placed a steel cylinder called Conshelf I at 10 meters depth in the Mediterranean. One man lived inside for a week. The following year, Conshelf II deployed at 11 meters in the Red Sea, housing 6 oceanauts for a month. In 1965, Conshelf III went to 100 meters, with 6 men living at depth for 3 weeks. Cousteau proved that saturation habitation worked. He also proved that it was prohibitively expensive, because every breath of every person in every habitat came from compressed gas cylinders shuttled from the surface by support vessels. The United States Navy ran the same experiment in parallel. SEALAB I, 1964, 58 meters, 4 aquanauts for 11 days. SEALAB II, 1965, 62 meters, 10 men across 3 teams for 45 days. SEALAB III, 1969, 183 meters, aborted when a diver died during deployment. The program was cancelled. The reason was not that the habitat failed. The reason was the same reason that would kill Aquarius 43 years later. The gas logistics chain, the support vessel, the compressed cylinders, the cost of keeping a human alive underwater using gas shipped from the surface. Between Cousteau and NOAA, there were other attempts. Hydrolab, operated by NOAA and the Smithsonian in the 1970s. MarineLab in the 1980s. The German underwater laboratory Helgoland. The Soviet Chernomor program. Each one demonstrated scientific value. Each one was ultimately limited or shut down by the same constraint. Not physics. Not engineering. Logistics. The cost of gas. This is the pattern that matters. The idea of undersea habitation has been proven 6 times over by 6 different programs across 4 decades in 3 oceans. The science worked. The habitats worked. The divers worked. The physics of saturation diving is fully understood. What never worked was the economics of keeping the gas flowing from the surface to the seafloor continuously for the duration of a mission at a cost that a research budget could sustain. Every one of those programs, if it had access to a self-contained membrane extraction system that pulled oxygen directly from the surrounding seawater, would still be running today. The habitats are not hard to build. The life support is not hard to design. The thing that is hard, the thing that has killed every undersea habitat program ever attempted, is the gas supply chain. That is the specific constraint the tow sled's core technology removes. The precedent is not a cautionary tale about ambition. It is a diagnostic report. 6 programs, 4 decades, 1 failure mode. The membrane extraction system addresses that failure mode directly. Everything else, the pressure vessel, the thermal management, the communications, the crew rotation protocols, was solved in the 1960s. The one thing that was never solved was gas. Consider the economics in concrete terms. A single saturation diving support vessel costs $15,000 to $50,000 per day to operate. A 30-day habitat mission requires that vessel on station for the full duration plus mobilization and demobilization, typically 35 days. At $30,000 per day, that is over $1 million in vessel costs alone, before any gas is purchased, before any science is conducted. The gas itself, the helium-based breathing mixtures used at saturation depths, costs $30 to $80 per cubic meter and is consumed continuously. A 4-person habitat at 20 meters depth consumes approximately 2 to 3 cubic meters of breathing gas per day. Over a 30-day mission, that is 60 to 90 cubic meters of gas, shipped in cylinders, transferred under pressure, managed by surface support crews. The gas cost is a rounding error compared to the vessel cost. But the vessel cost exists because the gas logistics require it. Remove the gas logistics, and you remove the vessel. Remove the vessel, and you remove the cost that killed every program. When the rat breathes in the sealed chamber, it is not the beginning of undersea habitation. It is the end of the problem that ended it. The first habitat, Part 4. The first habitat, the first undersea habitat powered by membrane extraction technology, will not look like science fiction. It will look like a shipping container. That is not a metaphor. The most practical near-term architecture for a small undersea research station at 15 to 30 meters depth is a modified ISO shipping container, a 20-foot or 40-foot standard unit, pressure-sealed and ballasted to sit on a prepared seabed pad. The container is a proven pressure vessel geometry. It is manufacturable by existing industrial suppliers without custom tooling. It can be transported on any flatbed truck, loaded onto any cargo vessel, and deployed from a standard crane barge. The life support system inside that container is modular. The membrane extraction modules, the carbon dioxide scrubbers, the thermal management system, the water reclamation unit. Individual components can be swapped by a diver working from outside the habitat during a scheduled maintenance window, without depressurizing the interior. The membrane modules are designed for hot swap replacement. A failed module is isolated, its inlet and outlet valves closed, a replacement installed in the same manifold slot. The habitat continues operating at reduced capacity during the swap. The oxygen supply comes from a bank of hollow fiber membrane contactors, the same Liquicell series used in the Phase 1 tow sled, scaled to 6 to 8 units in parallel. Power comes from a seabed cable connected to a surface buoy with solar and tidal current generation, or from a shore connection for nearshore deployments. There is no compressed gas cylinder in the system. There is no gas ship in permanent attendance. There is no countdown clock on the oxygen supply. The habitat supports 4 researchers in saturation for up to 30 days per rotation. Communications via acoustic modem and an optical fiber data cable bundled with the power cable. A 1-atmosphere observation blister, a transparent acrylic dome giving the interior a direct view of the surrounding environment. an airlock rated for diver entry and exit at ambient pressure. The total capital cost, the pressure vessel, the life support system, the power infrastructure, the deployment and seabed anchoring, is estimated at $4 to $6 million. That is the cost of a single well-equipped oceanographic research vessel, which has a service life of 25 to 30 years and operates continuously without the cost of fuel, crew rotations at sea, and port fees. The operating cost, once surface gas logistics are removed, is dominated by power and personnel. At nearshore deployments with a shore power connection, the annual operating cost is estimated at $400,000 to $600,000, 1/5 the cost of Aquarius, for comparable or superior scientific capability. This habitat exists. Not today, not in 5 years, but it is a direct engineering extension of the technology validated in the Phase 1 tow sled pool trials. The rat in the sealed chamber is its great-grandmother. The tow sled is its parent. The first habitat is the next generation. Scaling the atmosphere. Part 5. Scaling the atmosphere. The membrane extraction system scales linearly. This is one of its most important engineering properties, and it is worth being explicit about what linear scaling means. A single LiquiCell X50 membrane module, operating with PFC-assisted extraction at the efficiency parameters validated in the Phase 0 experiment, supports approximately one person's resting oxygen demand. A diver at exertion requires 4 modules in parallel. A 4-person habitat at rest requires 4 modules. A 20-person research station requires 20 to 25 modules. A 100-person underwater industrial facility requires 120 to 150 modules. In every case, the architecture is the same. Standard commercial components with a mature supply chain. The manifold plumbing scales by adding parallel branches. The pump scale by adding parallel units or upsizing to larger commercial impeller assemblies. The PFC recirculation loop scales by volume. There is no fundamental engineering discontinuity between the 4-module tow sled and the 150-module industrial station. There is more of the same thing, not a different thing. This is the core advantage over compressed gas at scale. Compressed gas systems scale catastrophically. A 100-person facility running on compressed oxygen cylinders requires a high-pressure gas farm that represents an explosive risk, requires continuous resupply from the surface, and fails catastrophically if the supply chain is interrupted. The membrane system fails gracefully. 1 module at a time. The remaining capacity maintains partial life support while failed modules are replaced. No surface gas supply required at any scale. At 100 people, the facility is an industrial installation, an offshore platform replacement for 30 to 60 metre depth operations, a deep-water aquaculture management station, a permanent seabed mining facility. The economic comparison is to offshore oil platforms, which cost $500 million to $2 billion to build and $200,000 to $500,000 per day to operate. A seabed-mounted facility at equivalent productive capacity, running on membrane-extracted oxygen with a seabed power cable, has a capital cost that is difficult to estimate precisely at this stage. The operating cost structure is fundamentally different. No drilling ship, no helicopter logistics, no flaring, no surface weather dependency. At 1,000 people, the facility is a town. The oxygen supply problem, the one the tow sled's core technology solves, is no longer the limiting factor. The limiting factors at that scale are thermal management, food production, psychological health, emergency evacuation, and political jurisdiction. Those are not trivial problems. But they are not the oxygen problem. The oxygen problem was the first one, the foundational one, and it traces directly back to the rat in the chamber and the membrane contactor that kept it alive. 1,000 people requires approximately 1 through 200 to 1,500 membrane modules running continuously. The LiquiCell supply chain, at current production volumes, could supply that system within a normal industrial procurement timeline. The technology is not the bottleneck at this scale. The will, the capital, and the regulatory framework are the bottlenecks. Those bottlenecks are real. We name them honestly. The autonomous ocean. Part 6. The autonomous ocean. Not every application of this technology requires a human occupant. The same membrane extraction system that keeps a researcher alive in a habitat can keep an autonomous seabed station running indefinitely. Powering sensors, communications equipment, AUV recharging docks, environmental monitoring arrays. No human presence, no surface gas supply. Script 2 described the AUV recharging application. Here it connects to a larger architecture, a network of autonomous seabed nodes, each powered by membrane-extracted oxygen feeding a hydrogen fuel cell, each capable of recharging and retasking autonomous vehicles, each collecting and transmitting environmental data continuously. The nodes are deployed by ship once and serviced by AUV on an annual or biannual maintenance cycle. No surface vessel in permanent attendance. No umbilical to a shore station. The network operates on seawater and whatever renewable energy source is available at each node's location. This is not speculation about distant technology. Every component of this network exists today, except one: the validated membrane extraction system that provides the oxygen for the fuel cell. That is the missing piece. The $150,000 rat experiment is the first step toward filling it. If Phase 0 succeeds, and Phase 1 validates the tow sled, and the aquaculture product line generates the revenue to fund parallel development, the autonomous seabed node is a Phase 3 or Phase 4 product, probably 10 to 15 years from now. The engineering path is clear. The funding path depends on execution at every prior stage. What such a network enables at full deployment is genuinely transformative. The ocean covers 71% of the Earth's surface, and 95% of it remains effectively unmapped at the resolution that would allow detailed biological, geological, and environmental monitoring. The reason is not that we lack sensor technology. The reason is that persistent deployment of sensor networks in the deep ocean is prohibitively expensive, using surface-dependent infrastructure. A self-powered autonomous seabed network changes that equation. Permanently. Not in the way that a single research expedition changes it, producing a snapshot of conditions at one place and one time, but continuously, at global scale, building a real-time picture of ocean chemistry, temperature, current, biological activity, and seismic behavior that has never existed before. The scientific value of that dataset is incalculable in the literal sense. We do not know what we would learn from it because we have never had anything like it. The policy value for fisheries management, climate modelling, tsunami early warning, deep-sea mining regulation is substantial and immediate. That network begins with the rat. It begins with the sealed chamber. It begins with the $150,000 experiment that tells us whether the metabolic loop closes on a living mammal without surface supply. Everything in this paragraph is downstream of that one result. The permanent settlement, Part 7. The permanent settlement, the furthest point on the map. The point most people assume is purely science fiction. Understanding why it is not science fiction, and why it is also not imminent, requires holding both things at once. A permanent undersea settlement, not a research station, not an industrial facility. A place where people live, raise families, work careers, retire. 5,000 people at 50 meters depth, or 50,000 at 100 meters. A civilization with a seabed address. The oxygen supply problem, the one the tow sled solves, the one the rat experiment tests, the one the Aquanautics Corporation failed to solve in the 1980s with cobalt shift-based compounds, is not the only problem standing between here and that settlement. It is the first problem, the foundational one. At 50 meters depth, the pressure is 6 times atmospheric. Human physiology at that pressure requires careful management of nitrogen narcosis, oxygen toxicity windows, and decompression schedules for anyone who surfaces. That is a medical and engineering problem separate from the oxygen supply problem. It requires its own solution, probably a habitat maintained at 1 atmosphere of pressure with a pressure lock interface to the ambient ocean, eliminating the saturation diving physiology entirely. Food production. A settlement of 5,000 people requires approximately 8,000 tons of food annually. Underwater farming, hydroponic modules, aquaculture tanks, algae cultivation can supply a meaningful fraction of that, but not all of it. Surface supply chains remain necessary for the foreseeable future. Energy. The membrane extraction system provides oxygen. It does not provide the kilowatts needed to power lighting, computing, manufacturing, and thermal management for 5,000 people. Tidal current generators, temperature gradient harvesters, seabed geothermal taps, and surface-connected renewable grids are all potential inputs. The energy architecture of a permanent settlement is a separate engineering program from the life support architecture. Governance. Who owns the seabed at 50 meters depth off a continental shelf? The UN Convention on the Law of the Sea has answers, but those answers were written for resource extraction, not permanent habitation. A settled undersea community generates legal and political questions that no existing framework addresses. None of these problems are solved. We name them clearly because the honest version of this vision requires naming them. The membrane extraction technology that begins with the tow sled removes one critical constraint, the oxygen supply constraint, that has made every previous discussion of permanent undersea settlement purely theoretical. It does not remove all the constraints. It removes the first one. The history of human settlement is a history of removing one constraint at a time. Refrigeration made the tropics habitable at scale. Air conditioning made the desert viable for cities of millions. Central heating opened the Arctic to permanent settlement. Each technology removed one constraint. The others remained until someone solved them too. The membrane extraction system is refrigeration for the ocean floor. It is not the complete solution. It is the technology that makes the question serious rather than fantastical. The rat in the sealed chamber is where that question becomes serious. The foundation holds, or it doesn't. Part 8. The foundation holds, or it doesn't. 3 scripts. 1 idea. Script 1. The 47-minute sealing has not moved since 1943. The physics of extracting oxygen from seawater is hard but not impossible. The components exist. The tow sled architecture resolves the weight and power problem. The Phase 0 experiment costs $150,000, takes 6 months, produces a binary answer. Script 2. If the rat breathes, here is what follows. The Phase 1 sled. The rebreather upgrade market. The aquaculture aeration product. The offshore inspection application. The AUV recharging platform. The honest roadmap from a sealed chamber to a first production contract. Script 3. If the foundation holds through every phase of work, here is the territory that opens. The first undersea habitat in a pressure-sealed shipping container. A 100-person industrial facility with no gas ship in attendance. A global autonomous seabed sensor network running on membrane-extracted oxygen. A permanent settlement at 50 meters depth, not this decade, not the next, but within the range of a human career from the day the Phase 0 experiment returns a positive result. The entire structure rests on the foundation. 1 rat, 1 sealed chamber, 1 membrane contactor. 1 question. Does the metabolic loop close on a living mammal, continuously, for 4 hours, without surface supply? If it does not, we stop. We publish the data. The engineering community learns exactly where the gap is. The $150,000 is not wasted. It purchases a definitive answer, and definitive answers have value even when they are negative. If it does, we have taken the first step toward the device that ends the 47-minute sealing. Toward the habitat that keeps Aquarius running instead of decommissioned. Toward the seabed network that gives humanity its first real-time picture of 95% of the planet's surface. Toward the permanent settlement that makes the ocean floor an address rather than an obstacle. All of it, every word of all 3 scripts, is downstream of one result. 1 rat, 1 question, 1 card to turn over. By CJ Run at Twitstrom. Look, listen or read in order to. CJ Run.